All right, everybody, welcome back. So in this section, we're essentially starting a brand new unit. We're going to be looking at hypothesis tests that are applicable when you have multiple categories. So this includes proportions and means. So in other words, more than two, so three or more. The first thing that I want to mention is that this is very natural. So for example, here is a short article that was written by Pew Research. So you can go ahead and select it to read the entire thing. It was posted a couple weeks ago, and essentially what it says is that it demonstrates that most Americans believe or approve of undocumented immigrants in the United States staying, but via some kind of like legal process. So, for example, if somebody is currently undocumented, then the majority of US adults, as you can see here, data shows that the majority of adults are in favor of some kind of legal process. And if you click the link, you can actually see what some of the requirements most Americans believe should be part of that process. So what I want to point out is that this is our entire population. So we've got our all Americans, and then we've got two different breakdowns. So one breakdown that is provided for us is using race as a qualitative variable to categorize our population. So we're essentially breaking down our population into smaller groups of more homogeneous blocks. One of them is, for example, white, Black, Hispanic, Asian. And you can see that if we look at that breakdown, that there is a difference in the proportion of people that agree. So you can see here is the percentage. So obviously you could turn these into proportion, who say that undocumented immigrants should have some kind of pathway. And you can see that there's also a difference in proportion in those who say that there should not be a legal pathway. So what we're looking at here is we're looking at multiple proportions. So if you were to pick one, for example, maybe you want to focus on reporting the favorable attitudes towards legal pathway to citizenship, or maybe just some kind of legal status, then this would be P1. This could be P2, this can be P3, and this can be P4. In other words, the proportion for that corresponding group that favors this. Now, we also have another breakdown, which is by ages. And you can see that, no surprise here, when we break this US population in two categories by age, that there is a trend that is observed here. So we can do the same thing where P1 would be the proportion of adults 18 to 29 who are in favor. Then the P2 would be the proportion of adults 30 to 49 who are in favor, and so on. So it's very natural for us to go ahead and say, can we analyze multiple proportions simultaneously? This is different from what we've done previously, where it was just P1 versus P2, where we compared whether P1 was different from P2, whether P1 was less than P2, and then finally, whether P1 was greater than P2. So that's what we've done previously, but that was just two groups. Now we're saying, how can I come up with hypothesis test for multiple proportions at the same time? And so the first thing that we want to do is take a look at the goodness of fit. All right, so the first test is the goodness of fit test, and essentially it allows us to determine whether a given distribution, so in other words, given data, we can find the distribution of our data and then determine whether that agrees with a claim. So here's an example. Just before we do anything differently. Let's say that this is the claim. So someone claims, so ignore the groupings here that they're different. let's say that this right here is the claimed grouping. So again, think back to hypothesis test. So pretend that we have group 1, group 2, group 3, group 4. So each of these different groups is a population. And the claim is that this right here is the distribution of our population broken up by group. So group 1 is supposed to be 77%, group 2 roughly 66%, group 3 57, and group 4 is 56. If this is the claim, we can go ahead and collect some data. So let's suppose that our sample results in this distribution right here. Then we can go ahead and say, does my sample support the claim that this is the supposed distribution of the population? And obviously here we can see that these bars don't really align at all. Like 77 is the highest here, 57 is the lowest there. So it's like, wait a minute, that doesn't quite seem right. Especially considering that the fourth and third group in my sample are higher than the third and fourth group in the claimed. So that right there means that there really isn't a lot of agreement between the claim, so the red distribution, and the sample, the pink distribution. And that's exactly what a goodness of fit test does. It basically says, is there a good fit between the claim and your sample? So there's two different cases. Let's go ahead and take a look at the first case. The first case is when the parameters are known. So this is going to be common for example, experiments or for production lines. And my first example is if you roll a die, a 6-sided die, then we know that if you roll the die and it's fair, then every number has a 1 out of 6 probability of being rolled. So after many rolls, we can then go ahead and say, does my sample distribution support that claim? So in other words, you will get a sample. I know there really isn't a lot of space here to write, but for that first one, you would get, for example, the side of the die, and then you can create basically a frequency chart or relative frequency chart. And we can say how many times was the 1 rolled, how many times was the 2 rolled, and so on. And so we know that roughly we should have these showing up around the same frequency. So for example, 166, maybe this one is 175. But then if 3 is, for example, shows up 45 times, just 45 times, and we're like, wait a minute, that doesn't really agree with the claim that each side, each number has a equal probability of appearing. So notice that these numbers, 166 and 175, they're kind of close to each other, right? Maybe they're very far away, but 166 and 175 are definitely closer than 166 and 45. So the under count for the 3 means that this sample right here makes it likely that the 3 maybe doesn't have an equal probability of showing up as number 1 and 2. So here the parameter is known because I understand the procedure that is generating my data. I'm rolling a die, and the claim is that the die is fair. Each side has an equal probability of appearing. Okay, so that's essentially what we're going to do. So notice that my sample does not provide evidence for this claim. So there seems to be a mismatch between my sample and the claim. Another one could be, for example, let's say you're interested in determining whether humans can really select at random. And one way you can do this is pretend that you're asking them to give you a suit. So from a deck of cards. Recall from our work in probability that there are 4 possible suits. There's the clubs, there's the spade, the diamond, and the heart. So if we wonder, if I ask somebody to give me a suit, is that going to be random, or is there going to be a different distribution? So here I know that it's known. So I can go ahead and just assume that it's going to be random. So I can go ahead and claim that each suit has an equal probability of appearing. So that's 1 out of 4, if it's really random. And because of the way the hypothesis tests work, I know that I'm going to assume, just for the sake of argument right now, that this is in fact random. Then I go out and collect some data. So I can just ask someone, hey, think of a deck of cards, maybe give them an example, and then ask them to pick a suit at random. Then the question will be, does the distribution of the sample demonstrate evidence that people are actually selecting this at random, or is there a preference for some suits over others? So there's actually an experiment you can think of. And notice that in either case, I know the probability of success in each case. So that's when the parameter is known. A lot of times, the parameter is not going to be known. So this happens a lot when you look at actual data. So in actual data, we don't know the true distribution. So an example of that is, think of a city, like for example, Glendale or LA County. And let's suppose that we have information about the demographics. In other words, the breakdown of race, income, education level, preferences, so on. Then what we have is we have a claimed distribution from data. Let's say GCC overall. Or actually, not GCC. Let's maybe make it just Glendale City. So we have information of the entirety of Glendale City. Then we're going to go ahead and say, well, I wonder if the distribution of, let's say, employees at GCC follows that same distribution. All right, so we're going to ask, do government offices, think of like, for example, juries. In this case, we're going to maybe look at GCC. Does that employ the same percent for each group? So it could be male, female. It could be the distribution of race, could be the distribution of, what's another one? Maybe zip codes. And in this case, notice that I don't know what the parameters are. What I do have, though, is I have a claim distribution from the data collected from all of Glendale. Okay, so here's an example. This one right here looks at marital status, so that's what we're interested in. And notice that for marital status, we have a bunch of different groups. So here's group 1, group 2, group 3, group 4, group 5, and group 6. Doesn't really matter what they are. And what we do is you can look at the distribution for all of California. So those are the little segments that you observe here. So for all of California, we're looking at this segment. So notice it's what is that? Maybe like a 38% or something versus LA County. So that's the lighter color. And LA County has 42% for that group for females. Similarly, if we look at widowed for California, we have this, which is roughly about maybe 6%, which is very close to LA County of 7%. It's a little surprising that if we look at divorced, for divorce, we've got this here. Versus divorced in LA County. So again, this gives you an idea of what the distribution should be because we're saying we have information for all of California. So now we're wondering if LA County follows the same distribution. And so here I don't have the numbers. The numbers for California come from data, right? It's not as simple as before where I knew exactly what that was. So this is going to happen a lot of times. We just essentially find the distribution ourselves. Another one that can happen is if you have a distribution that is known. So here there's a parameter is estimated from data. So this is using data. Here in the second example is where the claim distribution comes from a previous distribution, like for example, a binomial distribution or a Poisson distribution. And so in this case, we can still use stats calc and select our distribution, and that will be our assumed distribution that this follows. All right, so that's pretty much it. Let's yeah, I think that that'll be the end of this video. This just kind of tells you why we really care about this. And the next one, we'll take a look at the procedure that we'll be using.